Hello, this video is entitled Integration by Tables. Now in this particular textbook I'm using, these integration formulas are in Appendix B, but obviously they can be wherever, usually they're in the back somewhere. Well, this is, in other words, using integration formulas that we maybe don't normally use to integrate functions, certain functions. Now, one thing I want to make clear, the first thing I want to say is that for my students that whatever integral form, I'll put the required formula on the question on the exam. So in other words, you're not responsible for copying that entire integration table formula on the back or anything like that. I will use the appropriate ones. Now, sometimes there's ones where we'll see it might be a pair of formulas, like if a certain number in the integral is positive, you'd use the top one. If it's negative, you use the bottom one. So I would do that. Would give you where you have to choose the right one of the two. But the point being is you'll have some access, obviously where you can get the required formula. I say some access, you will have full access. You just may have to choose between two formulas to see which one's right. So let's just kind of play around with some of these, and some of these you'll see that they can be done by means we've already learned before. So I like to usually try to pick one on a test. It is something that would not be really that solvable by normal techniques. But this one, if you look, this is theta cubed over 1 plus sine of theta to the fourth, and using this form right here. Well, this form right here, we could have done from the section on basic integration rules by conjugation, conjugating the value. But I'm not going to do that, obviously. But here's what ends up. Now let's look at this plus minus versus this minus plus. Anytime you see this come up in an integration formula, that means the top one of the two goes with the top one. So if they're the same, plus would be plus and minus would be minus, if this was a plus on top and minus on bottom. But this is the opposite. So that means if you had plus here, you're going to use minus in the formula. If you have minus, you're going to use plus. So in this case, we have plus, and then therefore we'll use the formula with minus. Now these aren't going to be really overly difficult, but where people do mess this up is quite often is they don't appropriately adjust for the u and du. That's the key here. You have to adjust for the u and du to get this thing exactly right. Because it's real tempting just to plug it right in the formula and not even have to think about it. In other words, so yes, we are using this formula, but we have to identify is that u is theta to the fourth, therefore du will be 4 theta cubed d theta, and then 1/4 du will equal theta cubed d theta. So this theta cubed d theta is represented by 1/4 du. So we have to include that 1/4 if we want to make sure we get this problem exactly right. So yeah, that's very critical. And once you do that, it's pretty easy from there. So you use this formula with the 1/4 in front of it, and then now just replace u with theta to the fourth, and then we have it. Now here's one that's using a formula that could probably be integrated using trig substitution if we did it manually. But I don't want to worry about doing that, but it looks like we could. And the fact that the answer is not that complicated looking tells me it wouldn't be that difficult of an integral. But anyway, let's see what we have here. Now this e to the 2x might be kind of confusing on top. But what you want to think about, first thing to worry about is what does u need to be. Don't worry about any other stuff just yet. Well, if we have e to the 4x here, that means u would have to be e to the 2x, because e to the 2x all squared is e to the 4x. And then the derivative of e to the 2x would be 2e to the 2x. So you have 1/2 du equals e to the 2x dx. And there's where your e to the 2x is coming from up here. Even though it says from the 1, that's coming from your du. So we have a half that we have to include into this because of that du. So now we can say that we have 1 half du equals 25 minus u squared to the 3 halves. And then now it looks just like this situation right here. So it's going to be u, but in our case 1 half u. So it's 1 half e to the 2x. And then you have a squared, which is 25 on the outside. And then a squared minus u squared. So you have 25 minus e to the 4x on the inside to the 1 half. And I just kind of combine. It's not wrong if you don't, but I just combine the 1 half over the 25. And so it's 1 half times 1 over 25. So we'll leave a 50 down there. But just cleaned it up a little bit. And there's some Maple just kind of writes it like this for the ease. But that is correct. Now this one looks like it could be done by integration by parts, because that's how you would integrate arctan of u, is by parts. Once again, we're just going to worry about using the formula. So this one's not too bad, because obviously u has to be x to the 3 halves. And then when you take the derivative of it, you'll get that x to the 1 half, which is square root. But we have a 3 halves here, so we have to adjust for that and make that 2/3. And this is pretty easy. Plug this one in here. But see, I just left 2/3. You know, if it's a multiple choice question, you're picking an answer out on a test. You know, you may see the 2/3 distributed through here. Obviously, it doesn't affect the C, but so handwritten, this will be fine to leave the 2/3 factored out. So it's u arctan of u, so it's x to the 3 halves arctan of x to the 3 halves minus ln of u squared. Well, x to the 3 halves squared is x cubed. So it's minus ln of the square root of 1 plus x cubed. Now this one would be also trig substitution, but if you look at the right side of this, well, that would have been a pretty challenging integral by trig substitution. You see there's some complexity to this one. And this is probably a little bit overkill from what I would ask on a test. But anyway, you just kind of see by looking at this and giving you that formula, it's easy to see the u is 2x minus 3. So it's 2x minus 3. So the du would be 2 dx. And so you have to adjust that, makes a 1 half in there, and then a is 2. And you see this formula has a 1/8 in it. So this 1 half with the 1/8 makes 1/16. I'm not going to read out all those terms right there, but I think this one's a little over the top, but it's just it's a good example of using the formula. Well, when I say over the top, it's not complicated by any means. It's just got a lot of messy terms there, you know, so. Let's move on. How about this one? Now this one's kind of interesting because it has something that's called a reduction formula. This one looks like it could have been a complicated trig substitution maybe also. Now, of course, yeah, I don't think I would ever go higher than square here because this would just get really, really ugly. So if the n is 2 in this case, and we say reduction formula, what it does is you have a formula and then it still has an integral left, but you see when you get to this integral, it's reducing the exponent by 1. So it would work its way down. That's why it's called a reduction formula. So this would be extremely rude if that was like to the 5th power, because you'd have this first part, and then you'd have to do to the 4th. And you use the same formula again, then you have a 3rd. Again, a 2nd, again, you got down to the 1st. Because once you get this down to the 1st power, which we'll do that in one step here, that's just going to be an arctan. Because you're going to, the a squared, well, if it's not, I guess I shouldn't say that in case it's minus. And I guess it wouldn't be arctan. But if it's plus, it's definitely going to be arctan. I would probably certainly use plus here just to make sure. But anyway. So let's take a look at this. So you see, look at this, the u would have to be 2x to make it 4x squared. And then a is 5 and du is 2dx. So we have I didn't actually write it out, but I'm sure you would have figured out. So the next step would have said 1/2 du equals dx. So I have a 3, and now I'll have a 1/2 that comes from here. So that's where this 3/2 is coming from right here. So right there I have 2a squared n minus 1, n is 2. So I have 2 times 5 squared over 1 times 1. And then over here I have u over 25 plus u squared. And then that's going to be to the first power. And then we have 2n minus 3. Of course, with n being 2, that makes this a 1 right here. So that's why we don't see anything. 2 times 2 minus 3 is 1. And then I have du over 25 plus u squared. And we have to integrate that. We don't integrate the first part, see. First part does not have an integral with it. Reminds me a little of integration by parts. I like keyword being a little, only in the sense that you have a part that you don't integrate and a part that you do. But this is not integration by parts. So this is just straight out arctan right here. So it'd be 1/5 arctan of u to the 5th. So just everywhere we see a u, you replace it by 2x. So u is 2x, and then 20. The fact that obviously because it's addition, I can write this in either order. I don't know why I switched it, but I guess I made it look like the original problem. But 4x squared plus 25 is the same thing as this. And this antiderivative becomes 1/5 arctan of 2x over 5. And then all this mess reduces 3 over 2 over 50, just makes 3 over 100. So once again, in case you have to distribute 3 over 100, you could. I mean, I wouldn't insist on it, but if you're trying to match an answer. Maple did. Maple distributed it out there a little bit to get these numbers. So here's what I was just mentioning about the reduction formula. All right, so that one, like I said, I wouldn't make you do more than one reduction on that one, that's for sure. The next one, now here's one, I was mentioning this at the beginning of the video that, when I say I was going to give you the formula, I might give you something like this where it has this formula, but there's 2 choices based on a certain condition. That's what I was saying earlier. But either way, you're still not going to have to photocopy all the integration formulas and put them on your sheet or anything. Or if I'm not using a sheet anymore, if I'm providing the formula sheets, I better allow this to account for the future, because I've done both before. I've given formulas, and now at this point in time I'm making the video, I'm allowing students to use their own note sheets. So just in case I go back to the other, I don't want this video to be wrong. But I darn sure would provide this either way. So let's look at the integral. 5 dx over x, 3x, square root of 3x minus 4. Now it's kind of tricky because it's written a little bit backwards here, so you got to think carefully. Obviously the u is x, but you look at this and you have to think of this really as negative 4 plus 3x to make it fit this. So a little sneaky, because it looks like I gave you the wrong formula, like there should have been a plus or minus here, but no. This is negative 4 plus 3x. So that means A is negative 4 and B is 3. So the A is going to dictate which formula we're going to use, and it's the bottom one. You see the bottom one corresponds to A being less than 0. So our answer is going to be 2 over the square root of negative A. But since A is negative, that will turn it back into positive. And then arctan of this result right here. So let's see what we have. So here's what I'm saying, use the bottom formula. So we have a 5, just it's already there. And since u is x, du will be dx, so there's nothing to adjust for there. Just kind of wanted to mention that, because I guess it is possible that u could have been like x squared or something, and we would have had to adjust for that, the 2 from the derivative, but since u is x, du is dx. So I have the 5 from the problem and then 2 from the formula over the square root of negative 4. So that's the square root of 4, which is 2. So that just as that happens to be 4, these are going to cancel. And then you have arctan of, I could have put, either way it would have been fine. I just rewrote it in its original form, but I could have put negative 4 plus 3x, that would have been correct, over the negative of negative 4, which of course is positive 4. So either negative 4 plus 3x or 3x minus 4, all over 4, underneath the entire thing under the square root. And Maple got that, except Maple got cute. You know, they factored out that square root of 4 and brought it to the outside and made it 1/2, so don't worry about that. But that was kind of interesting. We had to choose between the two formulas. Here's another one. We have x squared minus 5x plus 2. And there's the formula. You see the terms are kind of reversed here. So be careful that you pick your A, B, C correctly. In other words, C would be 1, B would be negative 5, and A would be 2. So look at the comparison here. It's comparing, basically working with the discriminant. It's comparing the B squared to the 4AC. So very important to put your, like I said, put your numbers in the right place. So B is negative 5 squared is 25, and that would be greater than 4 from the formula, and then 2 and 1. So the 25 is greater than 8. So that means that is true. B squared is greater than 4AC. If it was less than, we pick the top one, but we use the bottom formula here. Okay, so actually I didn't show a lot of work here, but there's really not a lot to do at this point once we know it's the bottom one. And B squared minus 4AC would be 17, because it would be 25. Yeah, it's just moving this over to the other side. So 25 minus 8 is 17. And then C is 1, U is X, so it's 2X. And then B is negative 5, so it's 2X minus 5 minus that square root of 17. And then the bottom, it'd be 2X minus 5 plus that square root of 17. And the natural log of the absolute value of all that, plus C. And, you know, I could have shown a lot more examples, I guess, but this, it's just, you know, working with the formula that's given to you and making sure you do the U and DU appropriately. That's key. And then this case of adjusting, you know, or picking the correct of the two formulas. So with that being said, this concludes the video on integration by tables.